Okay, so our last speaker for the first day of the conference is Yuval Roichman from Bar-Ilan University. His talk title is Descent Enumeration and Pattern Avoidance. Please, Yuval.
Okay, thank you for inviting me and for this great conference. Okay, we'll speak about descent enumeration pattern avoidance from a certain algebraic viewpoint, and we'll explain. Okay, let's go over the basic definitions which were considered in previous talks. First of all, two sequences are order isomorphic if the corresponding letters have the same order, and permutation in the symmetric group Sn contains a permutation in Sk if it appears as a pattern or if there is a subsequent which is isomorphic to the sigma, so smaller permutation. For example, the permutation 2163454 in S6 contains 312 because the red letters have the same pattern. And we consider set of patterns, so let capital Pi be a set of permutation, and pi avoids capital Pi if it does not contain any permutation in capital Pi, and the notation is Sn. Capital Pi is the set of permutation in Sn that avoid pi or any pattern in capital Pi. Okay, statistics, we consider this descent set, which was considered in previous talks as well. So the descent set of pi is the set of positions where the entry decrease, the value decrease, pi I is bigger than pi I plus 1. So we consider the classical standard descent set. And the block number is the set of positions where all letters up to these positions are smaller from all letters from this position on. For example, if we take the permutation 23154 in S5, the descent set consists of 2 and 4 because second position, the letter in second position is bigger than the letter in third, letter in fourth position bigger than the letter in fourth. And there are two blocks because if we consider position 1, all letters up to the third position, if we consider the position 3, all letters up to the third position are smaller than letters from fourth position on, and here there are two blocks and no more. So this is, I think this was maybe introduced by Richard Stanley in another name, but it is very classical block number. So our main topic will be to discuss descent set, but block numbers will appear. Okay, we would like to study, sorry, I do not see the lowest row, but we would like, do you see the lowest row? We'd like to study descent set distribution pattern avoiding classes. And the language that we will use is the language of quasi and symmetric functions. And we are interested in very certain sets of patterns where there occurs a Schur-positivity phenomenon. Let us explain quickly. This was explained in Richard's talk. So we take a subset of permutation in the symmetric group Sn, and for each of them we associate quasi-symmetric function where there is Sn, so there are n indices. Each monomial is factor of n variables with n indices. Indices are weakly increasing and strictly increasing when j is a descent. And these are called Gessel fundamental quasi-symmetric function. And Gessel claimed they are implicit in all the Richard Stanley works, but they were presented by Gessel in '84. Okay, a subset of symmetric group is Schur-positive if this quasi-symmetric function is symmetric and Schur-positive. This reflects some symmetry of the set. It also reflects the fact that the set, there is a symmetric group linear action on the set, which is determined by the descent sets of the element. Okay, what does it mean to be Schur-positive? There are different characterizations which are equivalent. A is Schur-positive, as it was defined in the previous slide, if and only if there exists a negative integer such that this identity holds. This means that the descent set distribution over A is the descent set distribution over multi-set of standard Young tableau, where all Young tableau of same shape have the same multiplicity, same non-negative multiplicity M lambda. And there is also a third characterization in terms of relatively simple, let's say, existence of a character formula. We will skip this for this topic. Okay, so the main problem that we will focus on is to find Schur-positive pattern avoiding classes in the symmetric group. This problem was posed by Sagan and Wu in a certain paper or proceedings paper, but it was addressed before. And the early beginning of considering this question is maybe avoiding a decreasing sequence of length k. So it is well known that the set of permutations in Sn that avoids a decreasing sequence, subsequence of length k is Schur-positive. In fact, we know more that the quasi-symmetric function of this set, on this set is the multiplicity of each Schur-positive, each Schur function is equal to the number of standard Young tableau of the corresponding partition. And this could be proved, for example, using Robinson-Sennstedt-Knus, and this led maybe to the blossom, I can say, or to the beginning of this field of pattern avoiding with Richard Stanley and Herb Wilf conjecture that was using this formula and the Berel-Regev results, one can show that this set has an exponential growth when k is fixed, and this led to the conjecture that every pattern, the growth of Sn avoiding any pattern, single pattern, is exponential. And now in Budapest, this conjecture was solved here in Budapest, I think, when Marcus was in some visiting exchange students program. Okay, arc permutations. Now we are coming to less standard notions. So what are arc permutations? For us in this talk, arc permutations are permutations that avoid 4 permutations in S, 8 permutations in S4. These permutations are all permutations where the difference between first letter and second letter is -2 or +2. This set has different, also other characterization in terms of it has canonical Coxeter expressions. It also has geometric meaning, and the motivation to define this set arises in the study of triangulations. Anyway, so there are geometric and Coxeter characterization for this set, but we are interested in, now let's present, so all the set of permutation avoid in these 8 patterns is the set of arc permutation in Sn, and it was proved with a result that this set is Schur-positive, and the expansion is nice. It is essentially the Frobenius image of the exterior algebra of Sn-1 induced to Sn. So it's quite surprising that such a set has such a nice, carries such a nice representation. Okay, so and this phenomena was generalized to other pattern avoiding classes, or grid classes. These are classes which can be defined geometrically, and this was, and hint was illustrated in the first slide of such sets. There are large family of pattern avoiding geometric grid classes that are Schur-positive. Okay, let's go to another archetype. So our goal is to, okay, let's go to another archetype for me of pattern avoiding Schur class. So one archetype is the set of arc-permutation. Another example, interesting example, is the set of 3-to-1 avoiding permutation with prescribed block number. So this set is also Schur-positive. This was proved with Eli Bagno and Ronald Dean. And there is a nice expansion. And this is essentially not an induced restricted representation to, this is a restricted representation from S to N to Sn. Okay. So this is another archetype, and what our goal is to show that these two archetypes split to different notions of Schur-positivity when you try to extend them to other groups, other permutation groups. Okay. So now, before we go to group of sign permutation, I would like to mention a very recent result. So there was an extensive study of Sagan with different collaborators, Hamaker, Pavlovsky, and also Bloom. I think there are 3 or 4 papers about symmetry and Schur-positivity of pattern avoiding classes when the set of forbidden patterns is small. And there was a conjecture of Bloom and Sagan that was that was affirmatively solved by Avichai Mamo, student in Bar Ilan this summer, that if the set of forbidden patterns is not of size 1 or 2, let's say at least size 3, but all of them are in SK and their size is at most K minus 2, so the size is small, then there exists n such that the set is not symmetric, not that it's not Schur-positive, it's not symmetric at all. This was conjectured by Bloom and Sagan and proved by Avichai Mamo. So this is a negative result. If the set is small, the set of patterns is small, it could not be symmetric, not Schur-positive. And what's interesting with the proof is, I am now in Budapest, so the proof applies the Hungarian style of combinatorics. So the proof is using very different, how to say, type of theorems from extremal combinatorics, probabilistic arguments, and so there is a proof of existence in the like Erdős type combinatorics, and this is a place where Hungarian combinatorics could be used in the context of Schur-positivity. It's interesting for me, and I'm now in Budapest, and this is like the opposite direction that what was shown by Richard Stanley and the Rich Greenberg recent results, so that strengthening the enumeration of Hamiltonians on tournaments that was done here in any institute by, what is the name? Selle when he was student of Rede. So this was maybe the first proof of existence using probabilistic methods according to Alon Spencer book. And Rede used the more complicated methods to show that there is a node. And now how to say, Boston combinatorics beat the Budapest combinatorics, giving the explicit formula, not just the numbers. And this I'm also happy. So it's interesting to show that there is interplay between the schools. Okay, now let's continue. So we are coming to the second half of the talk, which will be shorter, but it may be more interesting for me and more recent results that show the difference when we try to generalize the positive phenomena, the phenomena of Schur-positivity on pattern avoiding classes in the symmetric group. One can ask, okay, we have arc-permutations and 3-to-1 avoiding permutations with given block number. Can we consider their Schur-positivity to the hyperoctahedral group Bn, Y group of type B, or the group of signed permutations, all bijections from -n to n, which map satisfy the even condition, this sigma of minus y, odd condition, sigma of minus y is minus sigma I. And the second, so we would like to find Schur-positive pattern avoiding classes in Bn. Okay, and here there are two questions. First question is to find the correct analog of pattern avoidance on Bn. This is the easier part, let's say. And the more ambiguous part or more challenging part is to find the correct notion of Schur-positivity for Bn. And this was approached by Poirier and Chow, what is not the notion of Schur-positivity, the notion of what are the quasi-symmetric, the fundamental quasi-symmetric function of type B. There are different approaches and we will consider them soon. Okay, so first example were the definite signed arc permutations. So what are arc permutations of type B? So if we remember, arc permutations of type A avoided 8 patterns, arc permutations of type B avoid 24 patterns. So these are 6 times 4, so it's 24. 24 patterns, meaning the relative absolute values are 1, 2, and 3, and the signs are the sign of the second element must be in the pattern negative. The first and the third are free. Here the sign is okay. We see this is the way that we define pattern avoidance in this case, and this is essentially, I will not mention it here, but this is going with the geometric, the triangulation or geometric interpretation or motivation to define arc permutation. Then there are, in the paper with Sergei Elizalde, we present 3 different arc permutation of type B. Some of them are related to the Coxeter structure, and they are not good for us. The one which is good for us is this one, and we denote the set of permutation in Bn which avoid these patterns by the set of signed arc permutation, A and S. And the theorem with Atanasiadis, Elizalde, and Onadin is that this set is Schur, type B, Schur-positive. What does it mean? That here we take the Poirier quasi-symmetric function. And if we sum over Poirier quasi-symmetric function, this is the Frobenius image of also induced in the symmetric group case, it was induced from the natural representation, exterior power of natural representation. In this case, it's also of Sn minus 1. Here it's also induced from Bn minus 1 to Bn. And this means that, so it's Poirier Schur-positive. Maybe the easiest way is not to define here Poirier quasi-symmetric function, but to explain what is the combinatorial essence of this statement, of this theorem. So the essence is the distribution of, we can ignore the word Cox stereo, the distribution of sequence, like descents of permutations, signed arc permutations, where they are considered as a sequence, as a series of length n, descents, and position, the set of negative positions. So these are two, so this is, here we consider two sets. Each permutation is associated with two sets. One, descent, when we have descents in the, when we read the permutation as a sequence, and the other one, when the set of negative positions. And if we look on the simultaneous, the bivariate distribution of these two sets over signed arc permutation, it is the same as the distribution of descents and entries in the negative tableau over the bitableau basis of this representation. So this is a representation of Bn, and there is a bitableau basis. So each basis element is indexed by pair of tableau of total size n. One is negative, one is positive, and the entries in the negative are they correspond to the positions of the position of negative letters in, and the descents are is when it's considered as the positive tableau is above, let's say, the negative tableau, the descents of the bitableau are the same as the descents of the signed arc permutation. Okay, so this is the first phenomenon. The second one. So now we will try to first to look on block number and 3-to-1 avoiding. So 3-to-1 avoiding permutations are the fully commutative elements in the symmetric group. This is known. It was proved. We will see soon who proved this. Okay, for a fully commutative element in Coxeter group, say symmetric group or hyperorbital group, and also other Coxeter groups, is the set of elements whose any reduced expression could be obtained from any other using commutations relations only. And we denote the set of fully commutative elements in W by FCW. And Billy, Jokush, Stanley proved that the set of permutations avoiding 3-to-1 is exactly the set of full commutative elements in the symmetric group, and the set of signed permutations avoiding these patterns is exactly the set of fully commutative of Bn. So characterization of fully commutative elements in Bn by pattern avoidance was presented by Stambridge, and not so simple, but fully commutative is a very clear notion, and clearly looking at the Coxeter structure of Sn and Bn, this is the correct generalization. Now, the disappointing fact is that the fully commutative in Bn are, this set is not Poirier Schur-positive. Oh, oops, so what should we do? Okay, however, it is a Schur-positive, meaning if we look on this generating function. Here we replace Fourier fundamental quasi-symmetric function, which was presented in his thesis under supervision of Rothenauer, by Chow fundamental quasi-symmetric functions, which were presented under supervision of Gessel, also in PhD thesis. Then this set could be, there is a nice expansion in terms of Schur functions. So this is, we call this Schur to be being Chow type B. So this is Chow type B Schur positivity. Okay. So what does it mean to be Chow? So we say that to be Fourier type B Schur positive, meaning that the descent set and negative set of negative position of negative values is in bijection with by tableau. Here, what does it mean? The distribution of Coxeter descents, that the Coxeter generating, so the shortening Coxeter generators of each element of each fully commutative element in Bn is prescribed block number of its inverse is equidistributed with Coxeter descents of by tableau basis of the corresponding Bn character. Okay, so there is so we see that when we speak about Schur positivity in Sn, there are two notions which could be hidden behind either Chow or Fourier. What is the difference? And we also see that Fourier Schur positivity, we can easily prove that Fourier Schur positivity implies Chow Schur positivity, because we also consider here the set of negative positions, which we ignore here. But the converse does not hold, for example, fully commutative elements. So what is the message of it? The message here is, I think that the question is, the set of pattern avoiding class, does it have a Coxeter structure or a structure as permutations, as let's say risk product structure, or as colored permutations? So if we consider the Coxeter structure, let's say for arc-permutations, then we will get the generalization will be Chow Schur positive, but not Fourier. If we consider the Coxeter structure, okay, and in generalize it, it's only Chow. If we consider the structure as colored permutations, or the geometric structure, then it is also Fourier. So anyway, what we would like to say that what hidden behind Schur positivity are totally two different notions, those caused by Coxeter structure and those caused by permutation structure. Those, okay. So I will thank you for the listening to the talk, and I wish you pleasant second day in the conference. That will be exciting as first day.
Thank you, Yuval. Very interesting talk. So we can take questions now. Any questions, please?
Okay, a very general question. You
Yes.
talk so much about Bn. I guess Cn is isomorphic to Bn. So what about Dn, for example?
Okay, for this reason, I'm now in Budapest to approach Dn. Combinatorics is more complicated, and there are also there is a good algebraic school here that. So we discussed this here. Now the Dn is what is discussed in this office in the last few hours.
It doesn't make sense at all to talk about the exceptional, exceptional group. Does it make sense, or it doesn't make sense?
Exceptional, it makes sense, and exceptional are even. I think exceptional, there are signs that are easier than Dn. Dn is like the combinatorics is complicated. It was there. I think it's not so known, but Caselli from Bologna has shown that to consider Dn, to understand the algebra, we should consider not complex reflection groups, but what he calls projective complex reflection groups. And the combinatorics of Dn correspond to the combinatorics of another index 2, or to the algebra of another index 2. So there is a like bijection between projective. There is a long paper in Israel Journal about projective complex reflection groups, and there you can see that there is a bijection between this group, like involution, where combinatorics of one is explained by the algebra of the other. And this is a game, okay, this is what I can say, not much. So Dn is a dream. Dn is much more complicated than Bn. So there is no Poirier. The theory of quasi-symmetric functions, I don't know, Richard, there are people on the audience, I don't know. If Ira is here, they can say much more.
Thank you.
Ira and Richard, they face this and their students. So I don't think this is as a nice theory, but there should be theory.
Anyway, the BN theory is already
Caselli and Marburg type of, I don't know. So this, we are now discussing this. This is what we are doing in this office. That's what we did this morning and tomorrow morning.
Thank you.
Any further questions, please? Okay, I guess we don't have any more questions, and also no more talks today. The organizing committee thanks all the speakers and participants. We listened to wonderful talks today, and we are looking forward to seeing you tomorrow. Thank you again.